There are a few implications to these Lorentz transformations, as we call it, that Einstein dealt with. Let's take for a moment, say, an inanimate carbon rod. The kind of thing that might save Homer Simpson in space one day. And let's assume it has a length of unit L, and it is moving to the right at speed v. Better yet, let's assume we have an observer who's moving to the right at speed v, as opposed to an observer who's stationary with respect to the rod. So if L is the length of the rod as measured by a motionless observer, what is the length of the rod as measured by a moving observer? Well, this moving observer is going to see the rod according to the speed of light. So it turns out nothing is instantaneous. Light comes from one end of the rod and light comes from the other end of the rod. And we're trying to measure how long that is. So our length is just a difference in the x-coordinates of the 2 points of the rod. And for this, in Newtonian mechanics, we'd have that x minus vt, and then say the other end is at 0. So we'd see a little bit of a length difference, not much. With Einstein, if we measure the two parts simultaneously where t is 0, in the past, with Newtonian mechanics, we would just have the length of the rod, no problem. If we do the same thing with the Lorentz transformations, that vt term still goes away. Right, 0 change in time, still going to produce that x, but we have a 1 over v over c squared. We have this function that is so common, it actually gets the symbol gamma for 1 over the square root of 1 minus v over c squared. Now, if you'll graph this in your calculator with v as the x-coordinate, you will notice that this actually changes the length of the rod. So let's say we have this L and the 1 minus v over c squared. Right. It's going to warp things when you have a moving observer. If your observer is stationary and the rod is moving, we have the opposite effect. We get what we call length contraction. So a moving rod has a length equal to L times 1 minus v over c squared, all under the square root. So as v approaches the speed of light, this gets closer and closer to 0. So when v is 0, L primed is L. So this point is L. We have our v-axis, and as v gets bigger and bigger and bigger, this gets smaller and smaller and smaller. So this is length contraction. Moving objects shrink in the direction of motion. Now that's as observed by a moving observer. That's not the way they see it in their own frame of reference. They see themselves as being stationary and the same size they've always been. So what happens if our rod is at an angle? If a stationary rod is at a 45-degree angle, then the distance along the x-coordinate is the same as the distance along the y. But if it moves in the x direction, now our x is going to shrink according to the speed v, our y is not. So this 45-degree angle is now greater than 45 degrees because it's now shorter this way than it is along the y-axis. So this compression in the direction of travel also means that objects appear to rotate perpendicular to the direction of travel as their speed increases. So this phenomenon is one of the first ones that gave people a distaste for relativity because it feels counterintuitive. We don't see this effect happening in our day-to-day lives. If you want to understand why, well, on highways, we move a little more than 30 meters per second. Let's be generous, call it 35 meters per second on the highway. Well, if we've got 35 meters per second, and we want to see what difference that makes in a 1 meter object, well, we take that 35 meters per second, we divide it by the speed of light, 299,792,458 meters per second. We square it, subtract it from 1, take the square root, and our 1 meter distance on the highway becomes, on a calculator that can support up to 13 decimal places, 1 meter. Because this fraction is so slight, when we square this, just this piece in brackets squared, that actually gives us a number of roughly 1.36 times 10 to the negative 14. So if we're going to measure this, even to 3 decimal places, then the square root of 1 minus v over c squared, we can tell by the function that it's always going to be less than 1. If we want to measure to 3 decimal places, we need that to be equal to 0.999. That differs from 1 in the 3rd decimal place. So fairly precise. Now let's take our 0.999 and square it. So this gives us 1 minus v over c squared equals 0.998001. So just slightly off. And that means our v over c squared is going to be 1 minus 0.998001, or 0.001999. So in order to measure this to 3 decimal places, our v over c has to be the square root of this, or 0.044710177822 and so forth. Which means in order to measure this to the 3rd decimal place, our speed needs to be approximately 134.03774 meters per second. So, counting off our digits here, we have to be moving at about 13,000 kilometers per second before we're going to measure even the slightest impact of relativity just based on the length contraction. So it didn't fit our intuition because our intuition does not prepare us for the regimes in which this takes effect. We'll deal with even less intuitive content when we deal with time dilation in our next video.